In this lesson, we'll cover how first and second derivatives affect the graphs of a given function. To start with, we'll need this definition. We call c a critical number of the function f if it makes the derivative equal 0 or the derivative not exist. To motivate the ideas behind this section, here I have some function that I've drawn which I'll call y is equal to f of x. On this function, I'd like to identify any critical numbers, that is, places where the derivative is 0 or is not defined. The way I've drawn this graph, the derivative exists everywhere, so I only need to check to see where the derivative is equal to 0. And I see there's a total of 1, 2, 3 places. That means there are 3 critical numbers on this function. There's one here, here, and here. And I'll call those numbers C1, C2, and C3. So 3 places where the derivative is equal to 0. These places are a point of interest on a given function because these places can be either local mins or local maxes. So, for example, are there any local min values on this function? And if so, where do they occur? And the answer is, well, there's 2 of them. Well, there is one at x is equal to c1 and also at c3, here and here. This is not the lowest spot overall on the function, but it is the lowest spot in some region around this number. This is a local min. Here, this is an absolute min, but it's also a local min as well. It's the smallest y value in some region around C3. Are there any local maxes? Yeah, at C2. This is not the largest value overall in the function, but in some region around C2, it is the largest y value. So one reason for focusing on these things called critical numbers is because they have to be the locations of a local min or a local max. The question is, how do you know if you have one or the other if you're not actually looking at a graph of the function itself? And it turns out you can use the first derivative of this function to completely determine this. Here's what I mean. A function is increasing or decreasing depending on whether the first derivative is positive or negative. So maybe just to state this as a fact, we've used this before. If your function's derivative is positive on an interval, then you know that the function f, the original function, is increasing. Likewise, if your first derivative is a negative number, this means that your function f of x is decreasing, provided that you're on an interval. Let's mark that on this graph. Where's the function increasing and decreasing? And I'll note if the derivative is either positive or negative. So like over here, the function is decreasing. What does this mean about the derivative? It's negative. Here the derivative is 0, but over here the function's increasing, and this means that the derivative is positive. This is enough to know that you have a local min value at this spot right here. Because your function is decreasing to increasing, there must be a lowest spot. If you focus on the derivative, that means your derivative went from negative to positive. Why is this a local max? Well, the function is increasing and then decreasing, meaning the derivative is positive and then negative. Therefore, there's a highest point here. If you're using just the derivative, positive to negative must mean there is a local max in this region here. And finally, looking at this last spot over here, the function is decreasing then increasing. Again, that means there must be some minimum value. If you're using the derivative, your derivative goes from a negative number to a positive number. These ideas are all summarized in what is called the first derivative test. Let C be a critical number, a spot like this, this, or this. If the derivative changes from positive to negative, then you know there is a local max at the value C. So that's here, for example. If your derivative goes from positive to negative, there has to be a largest value. Likewise, if the derivative changes from a negative to a positive number, it must mean there is a local min. That happens here and here. So to summarize, the reason we want to focus on critical numbers is because that will be the location of a potential min or a max. We can then use the derivative to determine which one it is. Let's use the first derivative test in example 1, meaning here's a function f of x. I'd like to find all the critical numbers of this function. Can we determine, using the first derivative test, which of those are mins and which are maxes. We'll also answer the question of on what intervals is the function decreasing and increasing. So to start with, let's find the critical numbers. This means we have to take the derivative of our function. The derivative is 12x cubed minus 12x squared minus 24x. This thing exists everywhere, so I only need to check where it's equal to 0. So where is 12x cubed minus 12x squared minus 24x 0? To solve this, I'm going to factor out a 12x. What's left over is x squared minus x minus 2. Furthermore, I can factor x squared minus x minus 2 as x minus 2 and x plus 1. There are 3 critical numbers for this function where each of these factors is 0. X equals 0, x is equal to negative 1, and x is equal to 2. So these are all critical numbers. What I'm next going to do is determine if these are mins or maxes. The way I like to do this is to draw a number line and graph where the derivative is 0. And I have 3 numbers where the derivative is 0. In order, negative 1, 0, then 2. Let's mark those down here. Negative 1, 0, and 2. This is where the derivative actually equals 0. If you want to use the first derivative test to classify these as local mins or maxes, the only other information you need about the derivative is it positive or negative in these other regions? I'm going to use a calculator to figure this out. I'm going to take my function f prime of x and plug numbers into it like negative 2, negative 1/2, 1, and 3 to see if I get a positive or negative number back. And I'll just note if it's positive or negative. So I'm going to do this in a calculator. So what I got is, for negative 2, I got negative 96. All I care about is the negative part of it. The derivative of my function is going to be negative to the left of negative 1. Between negative 1 and 0, I got a positive number, positive 7.5. All I care about is the fact that it's positive. When I plugged in 1, I got negative 24, so it's negative between 0 and 2. And then when I plugged in 3, I got 144, which is a positive number. So my derivative goes negative to positive to negative to positive. That is now enough to use the first derivative test to classify these as local mins or maxes. Let's look here. At x is equal to negative 1, the derivative goes negative, 0, positive. That means the original function is decreasing, then increasing. This means there is a local min. So I'll say at x is equal to negative 1, we have a local min. What about at 0? The derivative is positive to negative. That means your original function is increasing and then decreasing. This must mean x equals 0 is a local max. And finally, at 2, the derivative goes negative to positive, meaning the original function is decreasing, then increasing. There's a lowest point on the original function. Therefore, x is equal to 2. This is a local min. And that's it. We could actually graph the function if we wanted to see this, just to double check our work. I'll leave it just like this, that we can use the test to state these as local mins or maxes. There was another part to this question that said, determine the intervals on which f is decreasing and increasing. Again, we're trying to answer something about the original function itself. We can very quickly answer this by using this number line. Any place where the function is, the derivative is negative, the original function is decreasing. Any place where the derivative is positive, that means the function is increasing. So, where is f of x, let's say, decreasing? There's 2 intervals from negative infinity to negative 1, and also from 0 to 2. And the reason is those are the intervals where its derivative is negative. So whereas f of x increasing, these are the intervals where the derivative is positive. So from -1 to 0 and from 2 to infinity. That answers everything about this function in example 1. Let's try this again in example 2 to see if there's anything that we could potentially be missing. Will you always have a local min or a local max? So we'll use the first derivative test to define those places on this function. So the way to start this is to first find all critical numbers. So I'll take the derivative of my function, which is 4x cubed minus 15x squared. I need to check to see where this thing is undefined or equal to 0. This thing always exists, so I will just simply say I'm going to check to see where the derivative is in fact equal to 0. Okay, if I try to factor this, I can only take out an x squared, and it's equal to 0 if x squared is 0 or 4x minus 15 is equal to 0. There are two critical numbers for this function. X is 0, and also where 4x minus 15 is 0, or where x is equal to 15/4. These two numbers make the derivative, not the original function, equal 0. What I'll do again is draw a number line to represent the derivative. Where's the derivative? 0. I know all the places where that happens. And then I'll figure out around those numbers, where is it positive or negative? Well, it's equal to 0 at 0, and it's also equal to 0 at 15/4. Next, I just need to put numbers into the derivative to see if I get negative or positive numbers back. I'll try, I guess, -1, 1, and then maybe something like 5. When I tried -1, I got -19. All I care about is the negative part of it. Okay, it's negative. Between 0 and 15/4, I put in 1, and I got -11. So again, we get negative. If we're beyond 15/4, like at 5, I get a positive number. I should now be able to use the first derivative test to classify these as maybe local mins or maxes. Let's see what happens. I'll start with this one here. The derivative is negative, and then it's positive, meaning the original function is decreasing, then increasing. What does that mean? This means that x equals 15/4 is a local min. But what's going on here? Here the derivative is negative to 0 to negative. If you try to sketch the function, the original function f is decreasing, it levels off, but then it continues to decrease. So on the original graph, again, not the derivative, but the original function, around here, it's decreasing, 0 derivative, and then decreasing. Is this a min or a max? And the answer is, well, it's neither. This spot cannot be a minimum because there's values that are smaller than it on one side. It also can't be a maximum because there's values that are larger than it on the other side. It is possible that you have a critical number that doesn't fall into either of these categories. It's not a min, and it's not a max. I'll actually note that off to the side. X equals 0 is not a local min, and not a local max. It is neither. What happened is the derivative went from negative to 0 to a negative number. The other possible thing that could happen is your derivative is positive to 0 to positive, meaning your function is always increasing. In these two cases, you'll not have a min, you won't have a max. The only time that you can have a min or a max is if there's a change in sign from either negative to positive or positive to negative. It might be worth actually just doing a quick sketch of the original function itself, just to get a better look at what's happening on the original graph. When I put this into my calculator and I adjusted the window, I saw something that looked like this. It was decreasing, it leveled off, and then it kept decreasing. And it went down really far, but it did eventually come back up like this. This was the function for f. Here the derivative was 0, but it was not a local min or a local max. Here at 15/4, the derivative was 0, but it certainly was a local min value around 15/4. The second part of this lesson is using the second derivative to determine how that will affect the graph of a function. And so here I have some function that I'm going to call y is equal to f of x. And the thing to notice about this is, okay, sure, there's a couple of critical numbers, but you can use the second derivative to determine if there's some type of bending that occurs within the equation. Like here, if you look at this part of the graph from like here to about here, it's opening upward. There's an upward bend to the graph. And then maybe starting here and going in this direction, there's a downward bend to the graph. We refer to this type of bending in a graph as concavity, and specifically, we would call this portion of the graph concave up, and this portion of the graph concave down. Let me actually mark that here. So maybe from here and on, the graph is concave up. There's an upward bend to it. And then, from here to here, well, it's kind of bending downwards. This is what I'll say is concave down. There's a more formal way to define concavity. Concave up means if you pick a point and you draw a tangent line, because the equation is bending upward, it'll be above the tangent line that you draw. So maybe I'll just, as a location, I'll use this spot here. Notice that if you draw the tangent line, the function is above it, and here's where the graph is concave up. And you could also pick a spot here. Again, you draw a tangent line, and the function is above that tangent line. It's different over here if you pick this spot. You draw the tangent line, because the equation's bending in a downward direction. Okay, well, the function is going to be below that tangent line. And then same thing here. Draw the tangent line, the function's below it. Notice that there's a change from concave down to concave up. So I want to define one other term called an inflection point. I'm going to call this spot on the graph right about there an inflection point. This is any time that there is a change in concavity. At, we'll say, some number x. If a change does occur, we'd say, well, it's concave down, then it's concave up. Since there's some spot where that change happened, we call that spot an inflection point. Now the question is, without looking at the graph of the function, how could you use a first or second derivative to figure out when this occurs? And here I have a concavity test. On an interval, we have the following. If your second derivative is positive, that means your graph is going to be concave up. So this portion of the graph is equivalent to saying, okay, concave up, positive second derivative. So if the second derivative is positive, then your function f is concave up. And likewise, over here, the second derivative is negative. And therefore, your function f of x is concave down. Now, why would this happen? Here's the reason. If you look at this portion of the graph where it's concave up, notice the derivative is negative, it's 0, then it's positive. The derivative is increasing. If the derivative is increasing, then its derivative must be positive. Well, the derivative of the derivative is the second derivative. So an increasing derivative means a positive second derivative, and that's why if you have a positive second derivative, your graph is concave up. Likewise, over here, the derivative is decreasing. Notice it goes from a positive to 0 to a negative number. So definitely the derivative is decreasing. Well, if the derivative is decreasing, its derivative is negative, and its derivative is the second derivative. So if your second derivative is negative, that means your graph will be concave down. Let's now use this test to find where a given function is concave up or concave down. In example 3, the function f of x is equal to x to the fourth minus 3x cubed plus 7. Where is it concave up? Where is it concave down? And are there any inflection points on the graph? To figure this out, we need the second derivative, which means, well, we need the first derivative. The first derivative is 4x cubed minus 9x squared. The second derivative is the derivative of the derivative, which in this case is 12x squared minus 18x. I think the approach of determining where it is 0 will be helpful. I'm going to figure out where the second derivative is 0. I'll put those on a number line, and then from there I can figure out where the derivative is positive or negative. So where is the second derivative equal to 0? That's where 12x squared minus 18x is equal to 0. Here we can factor out a 6 and an x, and we have 2x minus 3 left over. The second derivative is 0 at 0, and also where 2x minus 3 is 0, which is positive 3 halves. So on a number line, I'm going to note that this is the second derivative that we're talking about. It's equal to 0 at 0, and also 0 at 3 halves. What we need to know is, where's this positive or negative? Any place where it's negative, it'll be concave down. Any place where it's positive, the original graph will be concave up. I'm going to put this into my calculator and plug numbers into it, like -1, 1, and 2. And I'll just note if those numbers are positive or negative. Into the second derivative, I put in -1 and I got positive 30. All I care about is the fact that it is positive. So I know that the original function is concave up here from 0 to negative infinity. Okay, between 0 and 3 halves, I put in the number 1, I got -6. All I care about is that it's a negative number, so the graph is concave down there. And then here, I put in 2, and I got a positive number, I got positive 12, but what I care about is the fact that it's positive. So what does this all mean? On this original function, where is it concave up? Well, that's any place where the second derivative is a positive number, which is from negative infinity to 0, and also from 3 halves to infinity. Where is it concave down? That's here, where the second derivative is negative, from 0 to 3 halves. So that answers that. The other question is, are there any inflection points? Meaning, are there any times where there is a change in concavity at a given number? And in fact, both 0 and 3 halves are inflection points. So I'll say there are inflection points at x is equal to 0 and also 3 halves. Technically, a point would also have a y value, but here I'll just note that, okay, well, at those two x values on the graph of the original function, there was a change in concavity from up to down and from down to up. Therefore, there are inflection points here. Let's now combine all of these ideas into a single example, meaning here I have some function f of x. I want to know, where's this thing increasing and decreasing? Are there any local mins or maxes? And finally, where's this concave up and concave down? And are there inflection points? We'll need to use both the first and second derivative to answer these questions. So to start with, the derivative of this function f prime of x is 6x squared plus 6x minus 120. Any question about increasing and decreasing, we need to know if the derivative is positive or negative. It's a good idea to figure out where it is equal to 0. So I'm going to set 6x squared plus 6x minus 120 equal to 0. I see that I can factor out a 6, and we have x squared plus x minus 20. And we can factor this as x plus 5 and x minus 4. There are two critical numbers on the function f. That's where the derivative is either undefined or 0. It's always defined, so I'm only going to check where it's equal to 0. The critical numbers are x is equal to -5 and also x is equal to 4. So on a number line, I'm going to graph where the derivative is 0. So one was at -5, another was at positive 4. I will now label, well, is it positive or negative here, here, and here? I'm going to enter this into my calculator and plug in numbers like -6, 0, and 5. So let's do that. When I typed in -6, I got positive 60, so I know the derivative is positive here. I then entered 0, and obviously I got -120, so this is negative. And then I plugged in 5, and I got 60 again, so we're back to positive. The derivative is positive, negative, positive. So where is f increasing? Well, that's on this interval and this interval because the derivative is positive here and here. So the answers are from -infinity to -5, but also from 4 to infinity. Where's the function f of x decreasing? Well, that's any place where the derivative is negative, and that's between -5 and 4. We are also asked for local mins or maxes, and we can answer that too. -5 and 4 are potential local mins or maxes. Well, the derivative goes from positive to negative. That's an increasing to decreasing function. So on the original function f of x is equal to 5 is a local max. So x equals -5 is a local max. And again, that's because the derivative goes from positive to negative. X is equal to 4 is a local min because the derivative goes from negative to positive, meaning the original function is decreasing, then increasing. So x is equal to 4 is a local min. The rest of this question asks about concavity, concave up versus concave down, as well as inflection points. So what we need now is to take the second derivative of this function and basically go through this process again. Figure out where the second derivative is 0, as well as positive and negative. So the second derivative of this function is, if we're taking the derivative of the derivative, we get 12x plus 6. This is a much simpler function. If we set it equal to 0, we get that x is equal to -6 over 12, and that is -1/2 or -0.5. On a number line, if we're looking at the second derivative, it's equal to 0 at -1/2. That's a potential location of an inflection point. I'm going to figure out if this thing is positive or negative on these two intervals. So this is a pretty simple function to use, but just to be consistent, I'll put it into my calculator, and maybe I'll put in -1. And what do you know? I get a negative number. And if you put in 0, also not a surprise, you get a positive number. Therefore, this is negative, then it is positive. What does this tell us about the original function? Where's f of x, let's say, concave up? That is here, where the second derivative is positive, from -1/2 to infinity. And where is the function f of x concave down? That is where the second derivative is negative, so from -infinity to -1/2. Are there any inflection points? Those will occur if there's a change in concavity, which there is. The second derivative goes from negative to positive. On the original function, it goes from concave down to concave up. Therefore, there is an inflection point. And occurs at an x value of -1/2. So just by using the first and the second derivative, we can answer all of these questions. One last thing to consider, is it the case that if the second derivative is 0, that you have an inflection point? And it turns out the answer to that question is no. Any place where there is an inflection point, the second derivative will be 0. But not every place where the second derivative is 0 will there be an inflection point. Here's a really simple example to see why. If you graph the function x to the 4th, it's a lot like looking at the function x squared, which looks like this. So here we go. Here's f of x is equal to x to the 4th. Without using any derivatives, just by looking at the graph itself, what do you think? Is it concave down, concave up? The answer is it's always concave up. It's always opening upward. There's this upward bend to it like this. So this is concave up on the entire real line. It's concave up everywhere, never concave down. So because it's always concave up, there's never a change in concavity. Therefore, there are no inflection points on the function x to the fourth. But you could still go through the process of, well, maybe I could take the second derivative and see if it ever equals 0. Does that happen? Well, we need the first derivative, which is 4x cubed. And the second derivative is 12x squared. Does this ever equal 0? And the answer is yeah. You can divide both sides by 12. You take the square root of both sides. The second derivative actually does equal 0 at x is equal to 0, which up here I'm calling that number c. So if you want, you could say, yeah, the second derivative is 0 at c is equal to 0. But there is no inflection point at this spot. It's concave up on the right and the left. There's no change in concavity there. Why did that happen? If you actually graph the second derivative and just compare where it is 0, positive, and negative, we just figured out it was equal to 0 at 0. Is it positive or negative to the left? Is it positive or negative to the right? You can put numbers in this function to see why. You could put in -1 and +1. Well, if you put negative or +1 here, you always get a positive number back. So it's positive to 0 to positive. There's no change in concavity. It's concave up because the second derivative is positive. The original graph, again, is concave up over here because the second derivative is positive. So a positive to positive means there is no inflection point. There's no change in concavity. The other thing that could happen is it could go from negative to 0 to negative, meaning the function was always concave down. Again, no change in concavity. This is something to look out for. It's very tempting to say any place where the second derivative is 0 will correspond to an inflection point, but that is not the case.